Okay, let's look at this next part of this section, which is, if you remember at the beginning, I said there was multiple ways to denote a vector, right? Different notations. And we're gonna look at this I plus bj vector. So those vectors. So we're gonna write vectors in terms of I and j. Or what did I say? Yeah, I and j. First, what are I and j? Well, I and j are what you call unit vectors. What are unit vectors? They are just vectors that have a length of 1. Now, why do we want a unit vector? Why do we want this I and j? And that is because the same reason why 1 is so important in arithmetic, right? We use it a lot with fractions. We use it a lot with different operations, because 1 is what we call the multiplicative identity, right? It's the number that you can multiply 1 to anything and it doesn't change it. So 1 is super powerful, right? Because it can become any number you multiply it by. And that's going to be super useful when it comes to looking at this notation. So this is what the unit vectors look like. So vector I, again, it's a vector of length 1. But more specifically, it's a vector of length 1 in the x direction. And then j is a unit vector of length 1 in the y direction. If I were to do a quick sketch of them, this is what they would look like. So we have, again, imagine this is length 1, vector I, length 1 is vector j. Now, how are we going to use that knowledge to rewrite the notation? Because every notation we've had is with these sort of inequality symbol looking. But we're going to switch it to I and j because, let me write this here. Okay, the vector a sub 1, a sub 2, right? These are just the x component, y component of a vector. Can be expressed in terms of I and j by, and this is what it's going to look like. So vector v can now be represented as a sub 1 I plus a sub 2 j. Now, how does this work, right? How are we able to just switch them right off the back? And the idea actually comes from how we talked about how adding works geometrically, right? To be able to add two vectors geometrically, you take the initial point from one vector and you put it on the terminal point of the other. And then you go from initial all the way to terminal to make your new vector. So what's happening here is, because these vectors have length of 1, this number here right? What does it look like when you multiply by a non-zero constant to a vector? We call this, or both of them, right? We call both of these essentially a scalar. Now remember, because I is a vector of length 1, the moment I multiply by any other number, it's going to become that length. So what happens here is I can make I into any length I want. And then I can make j into any length I want. And because we're adding them, I take the initial point of j and I put it on the terminal point of I. But the vector that's created, we have to go from initial I to terminal j, right? Which is pretty much how the representation vector work, right? We would go, let's say this was the vector 5, 2 from the origin, 5 right up 2, and this is the vector in question. Now with this I and j notation, well, the idea is I can have a vector, let me make it in bold, I can have a vector in the x direction, and that's essentially 5i. Because let's not forget, I is a vector of length 1, but because it has a length of 1, the special property about 1 in multiplication is that it can become whatever value you multiply by. So even though this vector has a length of 1, the moment I multiply by 5, it'll have a length of 5. And then I can add it with another vector of length 2. And this is going to be 2j. And then all we're doing, we're essentially just adding these two vectors together. Because if I add j onto I, that means I have to take the initial point of 2j, which is here, and I put it on the terminal point of 5i, which is, that's exactly what's happening here. So like if I move this, I'm taking the initial point of 2j and I'm putting it on the terminal point of 5i. And the vector that's created when you add the two vectors together, you go from the initial point of 5i and then the terminal point of 2j. And that is the vector 5, 2, or 5i plus 2j. So because of how adding vectors works, we can actually rewrite our vector in terms of these two unit vectors adding each other. But these components, which we called components before, I can use them to scale the vector to anything I need. So again, all this does is give us more representation, more notation of the vector. So let's do a couple examples. Again, these examples are just mimicking what we did before, but now they are tailored to this notation. So given the vector 3i plus 2j and the vector negative I plus 6j, we have to apply this operation. So and more so now, it really does look like distribution. It looks like I'm going to distribute. So 2u is going to be 6i plus 4j. And then 5v is going to be equal to negative 5i plus 30j. Now adding these two together, right, To add vectors, remember, all you do is you add the corresponding components with each other. So essentially 6 plus negative 5 is going to just be positive 1i plus, well, 4 plus 30 is going to give me 34j. I do everything the same, right? I just don't, instead of thinking about this vector as 3 comma 2, and this vector is negative 1 comma 6, again, we just add the corresponding coordinates. But of course, I had to apply this 5 first and this 2. But you add them the same. Same thing for the magnitude, right? If I was trying to find the magnitude of u, I will still be applying the same formula. I need to take the square root of 3 squared plus, oops, I'm already putting the answer, 2 squared. It's going to be the square root of 9 plus 4. That's going to leave me with the square root of 13. So again, these examples are just to get you used to this I and J format. Now, of course, this is great when you have those scalars, right? When we know the value of those scalars, because I then can scale I and J to the appropriate amount to have my vector in question. But sometimes maybe those components, right, those scalars aren't known. Luckily, when you think about making a vector, we're usually dealing with them in this diagonal orientation. Now, it was perfectly flat or perfectly vertical, then we know what our components would be, right? So my question was, what happens when we don't know these scalars? Well, if it was a vertical vector or horizontal vector, we would implicitly know particular components of those vectors, right? We know particular scalars, because if the vector was vertical, then the scalar for x is 0. If it was horizontal, then the scalar for y would be 0. But whenever we're dealing with a slanted, this is where we can actually go back to our trig that we learned, and that is, well, we could essentially make a right triangle. And the idea is I want to find my length, right? These are my scalars to help me draw my two vectors that I can use to find my overall vector. Now, how do I find these components and drawing a right triangle? Well, that brings us back to right triangle trigonometry, where cosine theta in question here would it be equal to adjacent over hypotenuse, which the hypotenuse is just the length of the given vector. And I can find that component by rewriting this into a sub 1 will be equal to, right, just multiplying the magnitude to both sides. I can write a sub 1 into the magnitude of v times cosine. And similarly, I can find the y component by, once again, or I'll just do it from the beginning. I can do sine theta, which is opposite over hypotenuse, which essentially is just the hypotenuse is the length of that vector. And remember, the length of the vector is found by the magnitude. So I can find these same components using our right triangle trigonometry, which that means I can write vector v instead of writing those inequality symbols, instead of writing a sub 1 and a sub 2, I can actually write that vector is, instead of writing a sub 1, I can write the magnitude of v cosine theta I, because again, that number is going to scale the vector in the x direction. And then a sub 2 will scale the vector in the y direction. So whenever that x and y component are given, luckily we know our trigonometry that can help us find missing sides of a right triangle. Now the next section I will talk about, and I'm not testing you on this, I just wanted to show you another notation. Testing for sure is on operations. Of course, for the final contains everything. So it would be working with these operations, magnitude, and so on. Now, one more thing to do is talking about the dot product, but I'll do that in the next video.